This video is just a matter of reviewing some practice problems that I found for calculating average atomic mass and basically how to navigate problems that you might see that are similar to or that are related to average atomic mass. There are a total of 7 problems. We're going to work through all of them. These are all short answer questions. Now, when you see an average atomic mass question, you might have a tendency that you want to go ahead and do a calculation, but you actually won't have to on all the problems that you encounter. For instance, this one, this really just requires you to review the periodic table. So this says that argon has 3 naturally occurring isotopes: argon 36, argon 38, argon 40. Okay, so if you look at the periodic table, this is going to provide you with all the information that you need. So if you look on the periodic table, you see AR. AR has an atomic number of 18. So what do we know about that? There are 18 protons and 18 electrons. And then you'll see the average atomic weight or average atomic mass. That is equal to 39.948. So that is the average atomic weight. So based on the abundance of all these different isotopes, 36, 38, and 40, which isotope exists as the most abundant in nature? Well, the answer to that can simply be looked at by comparing these 3 different numbers, the 36, 38, and 40. And what you need to do is simply see that, well, 39.948 is closest to 40. And so the most abundant isotope is AR40 because of the comparative atomic weight. This question is a good one in which you're going to be introduced to doing the calculation. We have 2 different isotopes of copper, Cu63, which is 69.17% of all of the isotopes known to man, and that has a mass of 62.9296. Now, that Cu63 is simply the 62.9296 rounded up. Okay, the other isotope is Cu65, which is 30.83%. Okay, and that has an atomic mass of 64.9278. Okay, so to solve the question, or to solve the problem of calculate the atomic mass, what we need to do is compare these 2 abundances. And to solve this, what you're going to do is put in parentheses 0.6917. Okay, so that's a fraction. That's 69.17. We are going to multiply that by 62.9296. Add to that, in parentheses, 0.3083 times 64.9278. Okay, now before we continue, one thing that we know that our answer is going to have is it's going to have nothing but 4 significant figures, because our 2 numbers, the 69.17 and 30.083, that's 4 sig figs. That's going to limit us. So I'm going to put in parentheses 0.6917 times 62.9296, close parentheses, plus 0.3083 times 64.9278, close parentheses. And the answer that I came up with here, based on this, is 63.545. Like I said, we've got 3 sig figs, so we want to get rid of that one. And instead, all that's going to do is just round us up to 63.55. That's the end of that problem. This problem right here is not so different from the previous problem. The only difference is that now we are working with 3 isotopes rather than 2. but the process is the exact same. What we do is we take the atomic mass, which we've been given with the three silicon isotopes of 27.9769, and our percent abundance, our mass abundance, our mass abundance. So what we're going to do is we're going to take 27.9769 times our percentage, which we are going to convert to a decimal, so 0.922297. I'm sorry, that 2 disappeared. 22297 plus 28.9765 times 0.046832 plus our final isotope. Our mass is 29.9738 times 0.030872 equals, put all that in the calculator, and what we get is, clear, 27.9769 times 0.92227 plus 28.9765 times 0.046832 close parentheses plus 29.9738 times 0.030872 close parentheses. Our final answer there is 28.085. And if you think about number of significant figures, well, we are limited by 5 sig figs. So our answer is 28.085. And if you compare this question to our first question, well, the most abundant isotope is approximately 28 AMU, and well, our answer came out to be very close to 28.0, or very close to 28. So it's not too difficult, it's just basically the same process. So gallium has two naturally occurring isotopes. The mass of gallium-69 is 68.9256. It is 60.108% abundant. The mass of gallium-71 is 70.9247, and it is 39.892% abundant. Calculate the atomic mass of gallium. 68.9256 times 0.60108 plus 70.9247 times 0.39892 equals 68.256 times 0.60108 close parentheses plus 70.9247 times 0.39892 close parentheses. Our answer is 69.72308. Number of significant figures, we've got maximum of 5 sig figs, even though this number has 6, so 5 sig figs. So our answer is 69.723. And that is our atomic weight, or our atomic mass of gallium. Bromine has two naturally occurring isotopes. Those isotopes are bromine 79, 78.918 is my mass of that, and is 50.69% abundant. Using the atomic mass reported on the periodic table, determine the mass of bromine 81, the other isotope of bromine. So what this means is we have two isotopes. Bromine Br79 and Br81. Okay, we're told that bromine 79 is 50.69% abundant. What does that mean for bromine 81? Well, that means, since there are only two of them, we know the abundance of bromine 81, and that is 100 minus 50.69, which means that this is 49.31% abundant. Okay, now the way that we've been solving these problems is we've taken the mass, which we have for bromine 79, 78.918. We've been multiplying those masses by the abundance. Well, in this case, we don't have the mass for bromine 81. However, we do have the mass for, or the combined mass of all of the, or I'm sorry, we do have the average atomic mass for the bromine isotopes, and that is 79.904. Okay, so what we need to do is actually set this problem up in a not so dissimilar way from how we've been doing our problems up until now. 79.918 times 0.5069 plus our unknown, which I'm just going to say is A, times 0.4931 equals 79.904. So what we can do for this, or the way that we want to approach this, is by multiplying 78.918 times 0.5069. That comes out to be 40.004. Now with that number, what I'm going to do is I'm going to subtract that from each side of the equation. So 40.004. Now whenever I subtract it from each side of the equation, that's gone, and now I'm left with 39.900. Okay, that is equal to, well, A times 0.4931. Now, if we want to figure out what A is, all that we need to do is divide each side by 0.4931. 0.4931. It's going to cancel over here, but if you take 39.9 divided by, or 39.900 divided by 0.4931, you're left with what A is. A, which is our mass of bromine, or Br81, that's an 81, that has a mass of 80.917 AMU. So this is not radically different from how we've been doing problems. It's just a slight variation of that approach. Calculate the atomic mass of lead. The 4 lead isotopes have atomic masses and relative abundances of this, that, and that. Okay, so this is a continuation on how we've been doing problems. 203.973 times 0.014 plus 205.974 times 0.241 plus 206.976 times 0.221 plus 207.977 times 0.524. Okay, now each one of these numbers, or well, actually what we can do is just plug all this in. 203.973 times 0.014 plus 205.974 times 0.241, close parentheses, plus 206.976 times 0.221 plus 207.977 times 0.524, close parentheses, and I came up with 207.217. I'm limited to 2 significant figures though, because if you look at this percentage there, well, that's going to, sorry, that would make this 2 significant figures. So chances are your number is going to be somewhere in the neighborhood of 207, 0.217. So that's how you do that. Antimony, which is Sb, has 2 naturally occurring isotopes. The mass of antimony-121 is 120.904 AMU, and the mass of antimony-123 is 122.904 AMU. So using the average mass from the periodic table, calculate the abundance of each isotope. So the average mass that I found on the periodic table is 121.760. Okay, what is that coming from? Well, that is going to be coming from one mass, the 120.904 times x, plus, well, 122.904 1 minus x. Okay. Now what you're going to do with that, since those two things, basically multiplying this by x and this by 1 minus x, that's going to present the differences. Okay. So what you need to do with this is kind of expand that. So 120.904 x plus 122.904 minus 122.904 x. Okay. Ultimately, this is equal to 121.760. When you combine all these variables, what you end up with is negative 1.144 is equal to negative 2x. Okay, so now when you solve for x, what you're able to do is say x is equal to 0.572. Okay, so what that means is x, or one abundance, specifically the abundance for the antimony Sb121, is 57.2, whereas Sb123 is an abundance of, well, the difference between this and 100, which is 42.8%. So this is probably one of the more difficult problems that you could face regarding this, where you're tasked with finding the percentages of each. But other than that, most of the problems that you'll see are basically not so different from examples 1 through 6. So good luck.